to make dark matter. And the most popular way, and in some sense the easiest way, is called thermal dark matter creation. And the idea for this is that you start off with a very hot early universe. In a very hot early universe, things bounce around and collide, and you have so much energy around, you can start, you have enough energy that you can more or less create any particle that interacts even a little bit. So the idea is that dark matter, we know it should interact, well, assuming it interacts a little bit with the regular particles, we're going to assume that the universe is hot enough that there's a thermal density of dark matter. Dark matter early enough on equilibrated with the rest of the universe and had some regular thermal density. But as the universe cooled off, the interactions of the dark matter with other stuff slowed down, and eventually the dark matter left thermodynamic equilibrium, leaving over a density that ends up being much larger than the density it would have if it had stayed in equilibrium. Yes?
What kind of interaction do we see?
Well, so we know that dark matter has to be electrically neutral and neutral under color, but for example, it can still have weak interactions. But it could also interact with regular particles in other ways that aren't necessarily the weak interaction. So there could be new forces, or we could even parameterize these interactions through higher dimensional operators. I'm not sure if you encounter that in your field theory course or your standard model course. But just about any interaction at all, as long as it's not tiny, 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 should equilibrate the dark matter early on, as long as the universe was hot enough. So for now, I'm going to, well, I'll come back to the specifics about dark matter, but the assumption for thermal dark matter is that the universe was once hot enough and the interactions with regular stuff were once large enough that the dark matter at some early point was in thermodynamic equilibrium with the rest of the universe. And then stuff happened. Further on, probably by tomorrow or Friday, I'll also talk about what's called non-thermal dark matter creation. And in this case, the dark matter may or may not have equilibrated with the rest of the universe. Okay, but again, the whole story here is going to be dark matter starting off in thermodynamic equilibrium and then leaving it. So I want to continue talking about what thermodynamic equilibrium means. And remember, whether or not a particle species is in equilibrium, we can describe the average properties of that particle species with a distribution function. So I'm going to use a distribution function that's a function of time, position, and momentum. I'm going to assume that my particles in the plasma are basically free particles and don't interact too much. So I can think of them as particles. And the characteristics of a given particle can be labeled by essentially its position at a given time, its corresponding momentum. So in equilibrium in the early universe, the distribution functions go over to the grand canonical ensemble distribution functions. And these should be familiar to you. And here I just have something with a chemical potential, a temperature, and minus plus 1, depending on whether it's a boson or a fermion. So this is the case for equilibrium. Now, we know that as the universe expands, it cools. And because of that, and we also know that the universe has a finite age. Because of that, our strict definition of equilibrium as a state that you reach after waiting an infinite amount of time can't apply. It can apply to the stuff in our universe, but in principle, it can't apply to anything else either. Even though we have that, we still can talk sensibly about equilibrium, provided the stuff that drives the system towards equilibrium happens much faster than the time scale that you've left the system to sit around. So, for example, if I take all the air molecules in this room and I put them over in the corner there, and I let them sit, they should bounce around and fill up the whole room in a kind of normal way relatively quickly. I don't have to wait for the whole age of the universe or an infinite amount of time to still talk reasonably about this stuff being equilibrated. So it turns out that in many cases, the stuff equilibrating these particle species does drive it to this equilibrium distribution much faster than the age of the universe, even when the universe was much younger. And because of that, we can describe stuff in the cosmological plasma as being in equilibrium in many cases. The only thing we have to take care of is that the effective temperature of a species and its chemical equilibrium are going to change as the universe expands. So for example, the universe expands and cools, and I can think of the cooling as the cooling of the photons. So if I use the photons to measure the temperature of the universe, it turns out that the photons follow a grand canonical ensemble distribution function, but with the temperature being a slow variation of time. So it's not a strict equilibrium, but the change in the temperature, well, the change in the distribution functions follows this equilibrium form with mu and t changing adiabatically. So for the most part, for stuff that we say is in equilibrium in the early universe, when we say it's in equilibrium, we're secretly saying that its distribution function follows the grand canonical ensemble with adiabatically changing temperature and chemical potential. Okay, so this is the case for equilibrium. What do I want to say? Okay, and there are two aspects to full thermodynamic equilibrium. And I'll talk more about this when I get specifically to freeze out. So thermodynamic equilibrium has two aspects. The first aspect is kinetic equilibrium. And kinetic equilibrium for everything just means that I have effectively, in this distribution, the same temperature for all species. So I could think about, so suppose I had two kinds of gas molecules. And suppose each kind of gas molecule interacted with itself, but not with the other kind of gas molecule. In that case, I could have one kind of gas molecule bouncing around in this room with one temperature, and the other kind of gas molecule bouncing around in this room with a different temperature. So the species with the higher temperature would have a higher average energy density than the species with lower energy. But these two different species, even though they're in equilibrium with themselves, would not be in equilibrium with each other. Now, what we want for full thermodynamic equilibrium is that these two species should also interact with each other a little bit. And once they start interacting with each other, the higher temperature species will transfer some of its extra energy to the lower temperature species, and everything will come out at the end of the day with the same temperature. So in other words, I wrote this distribution function with different temperatures for each species, but in full kinetic equilibrium, this means that each species in that equilibrium has the same temperature. So that's what I mean by kinetic equilibrium. And the thing that drives this kinetic equilibrium is elastic scattering between different particles. Because if I have one species that has a larger average energy than another species, the one with the higher average energy, corresponding to a higher temperature, will transfer some of its energy to the one with the lower temperature by elastic scattering. So that's the first one, kinetic equilibrium. And that corresponds to the same temperature. The second part is chemical equilibrium. And chemical equilibrium corresponds to the relative ratios of abundances. And the thing that sets abundances, the thing that sets the number density, are the chemical potentials. And what chemical equilibrium, well, the thing that sets chemical equilibrium are interactions in the plasma that transfer one kind of particle to another. So let me give you a specific example. Suppose I have a reaction where I have species A plus B plus dot, 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 being exchanged back and forth for species C plus D plus maybe some other stuff. So if this reaction, where A plus B plus stuff goes back and forth with C plus D plus stuff, if this reaction happens quickly relative to the time scale I've let the system relax over, I end up getting a relationship between the chemical potentials of mu A plus mu B plus dot, dot, dot become equal to the sum of the chemical potentials on this side. So this is what I get from chemical equilibrium, a relationship between the chemical potentials. Okay, so these are actually general features. but let's apply them specifically to the early universe. And in the early universe, our reference scale for temperature we set our reference scale for the temperature to be the temperature of the photons. So when we talk about the temperature of the universe, we're secretly talking about the temperature of the photons, and we measure all the temperatures relative to that. Yes?
In the chemical equilibrium, it can be that two different reactions are going on at the same time, but the two different sets of species are not interacting with each other. Therefore, they can be different. So what I'm saying is that is chemical equilibrium doesn't include kinetic equilibrium?
In principle, these are separate. So I instead of having two kinds of gases, suppose I had two classes of gases. Where class of gas 1 doesn't talk to class of gas 2, but stuff within class 1 talks to class within itself, and class 2 talks within itself. So there I could have separate equilibria in that case. Okay. But these are general results, but we're going to apply them to cosmology. So when we talk about temperature in cosmology, we secretly mean the temperature of the photons. The second thing is that observationally, today, photons, their distribution function is just a grand canonical ensemble as a function with energy, and they're observed to have zero chemical potential. So this shouldn't be surprising because we expected that in the early universe, you could have reactions that change photon number, and reactions that change photon number will drive the chemical potential to zero. Okay, so this will be our starting point. We have this relation, and now other stuff can, in principle, interact with photons, and this will modify what their chemical potentials are and what their effective temperatures are. So for any other particle, we can characterize any other particle we can characterize the energy of any other particle by its mass and its momentum. And the relation between the momentum of that particle and its mass and the energy is just this familiar one. So we treat them as relativistic particles. And where are we? Okay, so I'll come in a second to the distribution functions you get by plugging this energy relation into this grand canonical ensemble. But let me just mention quickly that in many cases, suppose I have a particle species, let's say I call it psi. In many cases, I can have annihilations where psi plus anti-psi go to, it can be interchanged to photons. So if this reaction is in chemical equilibrium, we have mu psi plus mu psi bar equal to 0 because the chemical potential of the photons is 0. So the upshot of this is that the chemical potential of a particle species is minus the chemical potential of its antiparticle. And one of the implications of this is that if I have a non-zero chemical potential for a particle that's not its own antiparticle, that implies that when I plug it in here, if this is non-zero, then I'm going to get a non-zero value here, obviously, but with a flip sign. And that means that when I plug it in here and integrate over d3p to get the number density, I'm going to have a different density of the particle versus the antiparticle. So a non-zero chemical potential for a particle that's not its own antiparticle corresponds to an asymmetry between particles and antiparticles. And we actually see this for baryons. For baryons, we see many more baryons and antibaryons, and we call this a baryon asymmetry. It's a puzzle how this arises, but it corresponds to a non-zero baryon chemical potential. On the other hand, in many cases, for a lot of other kinds of particles, we don't have a net asymmetry, so the chemical potentials are 0. And for a lot of what I'm going to do, I'm just going to set the chemical potentials to 0. And I'm usually going to do this for dark matter, with one exception that they'll come back and talk about a few lectures down the road. One other thing, though, is that suppose a particle is its own antiparticle. If a particle is its own antiparticle and it can annihilate to photons, then that implies that I get rid of these bars, and I get rid of the bar here. And the implication of this is that when I get rid of the bar here, if something is equal to the negative itself, that just gives me 0. So if I have a particle that is its own antiparticle, like a Majorana fermion or a real scalar, and it can annihilate efficiently into photons, that means that its chemical potential is exactly 0. And there's no asymmetry to talk about. Okay. So hopefully this stuff is stuff you've all seen in your cosmology course, but I just wanted to emphasize it and remind you of it here. So the upshot of this is now that I know what my so-called dispersion relation is, my relationship between the momentum and the energy, and I know what the equilibrium distributions are, I can write down what the number density is of a particle species in equilibrium. So for a particle species in equilibrium, I plug this energy relation into that grand canonical ensemble, and I take, remember, for the number density, I take d3p over 2 pi cubed times the distribution function. What I get for the number densities in equilibrium for species are therefore, I get either 1 or 3/4 for bosons or fermions. That corresponds to the difference, the minus plus, in the grand canonical thing. I get a factor GI, which corresponds to the number of degrees of freedom. Actually, I guess I should have put this in here. And I get some numerical stuff. I get a zeta function of 3 over pi squared, and then I get a t cubed. And this applies in the case of t much, much greater than the mass of the particle. And I've also set mu of the species to equal to 0. On the other hand, when the temperature is much less than the mass, I get a fairly different form. I get gi over mi times t over 2 pi to the 3/2 e to the minus mi over t. And this form should look familiar to you. This form should look familiar to you because this is just a Boltzmann suppression. So in the case when the average temperature is much less than the mass of the particle, we expect generally that the 3 momentum should be set by the temperature, roughly. And that means that the energy, if the mass is much bigger than the temperature, the typical energy of a particle is just a constant m. So it's completely dominated by the mass contribution to its energy. Its kinetic part is essentially 0. And this corresponds to just a regular Boltzmann suppression. This is just e to the minus e over t, just what you'd expect for a usual Boltzmann suppression. Now, the upshot of all this is that if I plot the equilibrium distribution as a function of 1 over t, and I'm going to divide by t cubed just for kicks. At early times, this thing is just a constant. So remember, by writing 1 over t here, as the universe cools, 1 over t gets larger. So this direction corresponds to the expansion and the cooling of the universe. So time is going in this direction. So this quantity is starting off to be a constant. But then when the temperature starts to become similar to the mass, I transition from this form to this form. And in this form, I get an exponential suppression. So very quickly, I go from this constant down to something that falls off very quickly and exponentially fast. Okay. So this is just the equilibrium story. Next, let me get on to departures from equilibrium, because this is where the interesting stuff starts to happen. Okay. So here we have, actually, just one more thing I want to point out, and this should be obvious, but keep in mind, remember, we're working in natural units. And in natural units, we're measuring, we set h bar and c equal to 1. And that means that we're measuring length in units of inverse energies and time in the same units as length in units of inverse energy. And that means our number density, which has units of 1 over length cubed, has units of energy cubed. And if you look here, this works out. So remember, temperature now has units of energy. We've also set the Boltzmann constant equal to 1. So this has units of energy cubed. That's what we want. This thing, this is dimensionless, but this thing has units of energy squared to the 3/2. This also gives the right dimensions. So keeping in mind dimensional stuff, it turns out that you can do a whole lot just with the dimensional analysis in cosmology. It's really handy. Okay, anyway, back to departures from equilibrium. Okay, so in general, our distribution functions work whether or not the species is in equilibrium or not. In equilibrium, though, the distribution function transfers over to this grand canonical ensemble version, where the grand canonical ensemble version is time independent, except for an adiabatic change in mu and t. When we go to departures of equilibrium, we're going to lose that form, but we're going to keep the distribution function idea. So again, I spoke about chemical and kinetic equilibrium. And one general implication of kinetic equilibrium, in general, is that when you have kinetic equilibrium, the relative fractions, the relative fractions as a function of energy should keep the same form. So in other words, a more precise definition of kinetic equilibrium is that your distribution function is now given by some constant function of time alone times okay. So it turns out that if you have chemical equilibrium, if you have kinetic equilibrium, but not necessarily full thermodynamic equilibrium, you can still write your distribution function in this slightly modified form, where the relative weighting as a function of energy takes the same form, but you can have an overall difference that's time dependent. So this piece just matches up with what we had here with adiabatic mu and t's. In this case, the Ti is given by the universal T corresponding to the photon temperature, but you can have a variation, an overall prefactor variation that doesn't change the relative weight of the distribution, but it can move it up and down. It's a function of time. So this will be the implication of kinetic equilibrium, and we're going to use this in a little bit. Yes? In some sense, this is the definition of kinetic equilibrium. So yeah. So again, the idea of kinetic equilibrium. So here's an example. Suppose I have my two species of gases, and these two species of gases can interact with each other, but I pump a whole lot more species 1 of gas than species 2. In that case, because they can interact with each other, they'll reach the same temperature, but they won't be in chemical equilibrium because I'll have a larger amount of one than the other. So the point there is that the distribution as a function of time will take the same form, but I can have an overall prefactor corresponding to scaling the other species up. Okay. So again, this is sort of a technical point, but we're going to use it in a little bit. Now, chemical equilibrium, I don't have anything as nice to say about this, but let me move on generally to how you compute going to and from equilibrium. So whether I'm not in equilibrium, to describe going to equilibrium or leaving it, I write down something called a Boltzmann equation. So a Boltzmann equation is an equation that is essentially a set of differential equations for the distribution functions. And in the limit that I let these Boltzmann equations go on for a long time, they should asymptote to the equilibrium values. So the form of the Boltzmann equations that are going to describe the distribution functions going to and from equilibrium. So I'm going to start off by just writing a formal general form. And this formal general form has two pieces. And I'll tell you what they are in a second. Mhm. So Li. Okay, so this is the Boltzmann equation for the ith species. And the stuff on this side, this is called this is called the Liouville term. And this piece only depends on the distribution function of that species, the Fi. Whereas the second piece is called a collision term, and it depends on the distribution function of that species plus any other species in the plasma. And the idea is that this piece is going to turn out to be essentially a time derivative of the distribution function, whereas this piece is going to account for collisions and interactions that change the distribution function. So the first term, the so-called Liouville, so the Liouville term, in a non-relativistic system, it turns out that the Liouville term is essentially just a total time derivative. It's a partial time derivative plus so you should recognize this as just it's just a total time derivative with respect to time for something that depends explicitly on time or through time or on time implicitly through x and p. So in other words, this is just what I would think of as a total time derivative. So this is Liouville specifically in the non-relativistic case. And we want to generalize this to the relativistic case, also accounting for possible departures from flatness of spacetime. Because remember, we have a warping of spacetime from the Hubble expansion. So in the relativistic case, I should say the general relativistic case, the Liouville term takes a slightly fancier term, a slightly fancier form, but it still is morally the same thing as this. And in the relativistic case, and this is the one we're going to use here for cosmology, L of Fi is going to be P alpha del x alpha minus gamma alpha beta gamma P beta P gamma del P alpha acting on Fi of T, X, and P. So this piece generalizes this in a simple way. So this momentum, up to essentially a mass factor, just corresponds to what I would have here. So this thing looks like a velocity, and this thing looks like a mass times d dt. So in the non-relativistic limit, up to an overall mass factor, this p, for the zeroth component, just reduces to the mass of the particle times d dt. For the spatial components, it reduces to the spatial momentum, or it reduces to mass times velocity times d dx. Again, that corresponds here. And this last piece with the momenta, it again coincides with what we had here, but there's an extra correction from general relativistic stuff. So this piece is just a Christoffel symbol. So this general form is still a bit of a mess. But when you plug in the Christoffel symbols for an FRW universe and put in various stuff, this form simplifies a lot. Okay, so this is the Liouville term. Now, when I apply this to cosmology, we have FRW. And one other thing I can do to simplify my life is integrate the Liouville term over d3p of that species. And when I integrate it over d3p of that species, what I end up getting from here, after some fiddling, is this Liouville term reduces for my species I a dni dt plus 3h n chi. So this piece reduces to this, and on the right-hand side, I have this collision term. I'll tell you what the collision term is in a second, but doing the same thing to the collision term, I'm going to get some modified collision term that I'm going to write as c tilde of fi, and possibly also all the other distribution functions. Oh, sorry, should be an I. Okay, so just very quickly, what's going on here is that here are the collision term. This is a Liouville term, and suppose I set this piece to 0. If I set this piece to 0, that corresponds to turning off all the interactions of the particle. And what I see in that case is the number density in that case, the number density dn dt is equal to just minus 3h ni. But remember, the Hubble constant is just a dot over a. And it's not too hard to solve this, because this side looks like a total time derivative. And the result of this is that my number density, ni of t, in this case, is just proportional to a to minus 3. So in the absence of collisions and interactions, I see that my number density of a particle species from the Liouville term with this relativistic correction just redshifts with the expansion of the universe. So in other words, the number density, suppose I take a fixed box of coordinate radius and I put a certain number of particles in there. Since there are no collisions, that number of particles will stay the same, but the size of the box gets bigger, and that means the number density gets smaller as an a to the minus 3. Yes?
Would quantum mechanical effects change that, like because of particle creation, quantum field theory effects of curved space-time? Would that change? This is a classical result, right?
Yeah. So
in
yes.
some sense.
So I could say that. So I could say that here I'm looking at an ensemble of lots of particles,
Right.
And these Boltzmann equations are strictly classical. As far as the expansion of the universe goes, it's typically mild enough that I don't have to worry about these strong quantum effects. Okay. There are situations where you do, but this won't be one of them. And in principle, I think the way those would often be handled is just dumping them in here. Actually, one other thing is, actually, in the quantum mechanical case, this Liouville term is local in the sense that I can write it as just some differential operator hitting the distribution function. In the full quantum mechanical case, it might not even be entirely local. So it gets to be a bit messy. But we're not going to have to worry about that for us. This formalism will be enough for what we want. Okay, so I'm going to start to specialize. I'm going to start to specialize keeping dark matter in mind. And for dark matter, I'm going to call dark matter chi, just for fun. And I'm going to start to talk about the collision term. And for the collision term, this modified collision term, suppose I have a process in the plasma that changes the number of chi. Suppose my process is chi plus A plus B plus dot 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 being exchanged with particle I plus dot 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 plus particle J. So suppose I have this interaction happening. This interaction gives me a contribution to this kinetic term, this collision term C tilde, and the contribution from this interaction to delta C tilde for chi is given by a long and slightly complicated expression that's actually not as complicated as it looks. So I'm going to write it out, but please bear with me. It's going to be essentially an integrals over space. So I have an integral over the phase space. I'll tell you what these d pi's are in a second, but they're essentially just d3p's. I have an integral over the phase space of the initial states. And I have an integral over the phase space of all the final states. I'm going to have an overall energy momentum conserving delta function, 2 pi 4, delta 4, p chi plus pa plus pb minus pi minus dot dot minus pj. Okay, so continue on to the next line, times a 1 over s times m tilde chi plus b goes to I plus j. So this is going to be the quantum mechanical matrix element for this transition. And I multiply this quantum mechanical matrix element by all the distribution functions. And so this is for the forward reaction, where I have the chi plus a plus blah, 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 goes to I plus blah, blah, blah to j. So here I multiply this forward matrix element by these distribution functions of the initial state. Whereas for the final states, I have 1 plus or minus fi for all this stuff. And then I subtract off the distribution function for I plus dot, dot, dot plus j goes to chi plus dot, dot, dot plus b. And I multiply this by fi times all the way to fj, 1 plus or minus f chi, 1 plus or minus fb. And then I close my bracket. So the stuff going into here, let me just list it all here. The d pi I is just a phase space factor. It's just equal to the number of degrees of freedom of the I species times d3 pi over 2 pi cubed times 2 ei. The f's are just the distribution functions. And the matrix element, m tilde, for I to the f squared, is just the usual squared quantum mechanical matrix element you compute in quantum field theory. But the one twist on it is that it's, remember in quantum field theory, you did spin sums, where you're either averaging or summing over all spin states, and possibly other states like colors and charges and so on. In this case, the special thing about this is you average over both the initial and the final states. So it's the usual summed in squared matrix element you have, but you're averaging over both initial states and final states. So we average it over both initial and final states. Okay, so there's a lot going on here, but this should start to, yes? Oh yeah, I forgot the s. The s is a symmetry factor. Yeah, so the s, the s means that I have a factor of 1 over n factorial for all identical initial or final things. And you actually get the same symmetry factor when you compute things like cross sections in quantum field theory. So on top of the summed in squared matrix element, if I have identical final states, I also have to add a symmetry factor to account for the fact that they're quantum mechanically indistinguishable. Okay, so again, this is a long, messy result, but it should start to look a little bit familiar to you. So for example, if I didn't have these distribution functions, and I didn't have this integral over the initial phase an initial state phase space, this would look a whole lot like a scattering cross-section. On the other hand, because I'm not just computing a scattering cross-section, instead I'm computing this contribution to the change in this case, the number density, I have a bit of extra junk. And that extra junk coincides with the fact that I now also sum over the initial phase space. I have my usual 4 momentum conserving delta function. These p's are the 4 momenta. This is the matrix element for the forward reaction. And this matrix element for the forward reaction is weighted by the distribution functions of the initial states. And this weighting makes sense because the larger the density of the initial states, the bigger the contribution to the forward reaction I'll have. These additional factors are purely quantum mechanical. In most cases, it's going to turn out that these distribution functions are much less than 1, so this stuff just goes to unity. But the reason for these pieces comes about because the plus sign is for bosons, the minus sign is for fermions. For a minus sign, what's going on is as the distribution function goes to 1, that means that in my final state phase space, I'm filling up that phase space with fermions. And because I can't put too many fermions, I can't put more than one fermion into the same quantum state, this accounts for the fact that as I start filling up the final state, I can't have the reaction go anymore. So this is called Pauli blocking, and this minus sign corresponds to that Pauli blocking. On the other hand, the plus sign corresponds to a Bose-Einstein condensation, where if I have lots of bosons, well, bosons like to hang out, so lots of bosons in the final state is great for making more bosons. So these are quantum mechanical, either Pauli blocking or Bose-Einstein factors. This is weighting by the initial phase space for by the distribution functions of the initial state. And then if I look at this reverse piece, this just tells me about the reverse reaction. So for the reverse reaction, I have I plus j, blah, 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 goes to that. And now I weight by these initial state distribution functions, and I have these quantum mechanical factors here. Yes?
I missed why you're using delta C.
Okay, so this is the contribution to the collision term from this reaction alone, but I may have other reactions that also change the chi number. So the total C tilde is the sum of all these delta C's. So this is just the one contribution, and you have to do a similar contribution for every single reaction. So it can get a bit hairy if you have a lot of reactions, but at least physically, hopefully this is somewhat intuitive. And again, the idea is that suppose I look at my number density of chi. Suppose I have less chi than I would expect. If I have fewer chi than I would expect, if I have fewer chi than I would sort of naively expect in equilibrium, then this factor will be small. And if this factor is small, this forward reaction is slow, whereas the reverse reaction is faster. And this reverse reaction, I have a minus sign here, and take note of this minus sign here. I probably should have flipped it, but this minus sign plus this minus sign means that together, this term, if it's dominating over this term because this is small, I'm going to get more n chi's. I'm going to get more chi's, and I'm going to increase n chi through the differential equation there. So the point is that these terms either push up or push down the number of chi's in a reasonable way. So a larger distribution function corresponds to more chi's, and a larger distribution function means that this piece is bigger, and with this minus sign, I end up depleting the chi's. So it's kind of a messy equation, but the physical content, hopefully, is somewhat clear. Okay, so this is still a mess, but the good news is that in a lot of cases, we can simplify the mess a whole lot. And this is what we're going to do for dark matter freeze-out. And we're going to essentially simplify this thing until I can make it look like a scattering cross-section. Okay, so the first part of that is that, so in the cases that we're going to be interested in, usually the distribution functions are much less than 1. So the upshot of that is that all the 1 plus or minus factors, I can just replace by unity. So this makes my life much easier. The other thing is that these squared matrix elements for the forward and reverse reactions, for this reaction to be different from this reaction, I have to have CP violation. And CP violating effects require an interference between a tree level and a loop contribution, plus other stuff, and they're typically smaller than the non-CP violating contributions. So the effects of CP violation for what we're going to do are usually either not present at all or very subleading. So we're going to assume either no or little CP violation. And the implication of this is that the forward and reverse matrix elements are going to be the same. And that means we're going to be able to factor them out of this expression. And I'm just going to call this m tilde squared for that reaction. OK. So now if we plug all this stuff back in, we get a simplified form with these approximations. We get a delta c tilde equal to this integral over the initial phase space, integrals over the final phase space. And now instead of having that big mess, I just get a 1 over s, m tilde squared. I'll put a minus sign here. And here I just get fa, fb, minus fi, fj. Okay. Oh, and then I throw out my delta function. Okay, so my life is now a lot easier, really somewhat easier. And I've reduced this thing to something that I know how to compute quantum mechanically. You just draw your Feynman diagrams and sum in average over spins, and I get this. So you know how to compute this. These distribution functions are still a bit messy, but it's going to turn out that when we integrate over these phase spaces, we can turn the distribution functions into things that look like number densities. So where are we next? All right. Okay. Yes.
So in principle, these distribution functions we have to figure out by solving all these equations.
Yes. Yeah. But the cheat we're going to make, and this is usually a good cheat, is that at high temperatures, we know that stuff in the standard model stuff interacts with itself pretty efficiently. So at high enough temperatures, all the standard model stuff we can just set to the equilibrium forms. So what we're going to end up doing is that everything except for the dark matter distribution function, we're going to set to the equilibrium value, and that's going to let us factor out everything except for an equation for the number density of the dark matter particle. Yes. Oh, sorry. This is all minus. So it's just the overall delta function. Right. Sorry. Yes. Yes. Okay, so this matrix element corresponds to this initial reaction, but with specific initial and final state momenta. If I apply, how's it go? If I apply parity, parity has the effect of flipping all the momenta. And if I apply charge conjugation, I flip the order of initial to final. So I change. Sorry. If I flip, sorry, I'm getting confused. If I apply charge conjugation, I change this reaction into one between the antiparticles. And now if I flip the momenta, I also flip the momenta. I've changed each initial and each final momentum to negative of its value. But it turns out that that thing is equivalent because we know that we expect that CPT, the full CPT invariance of the theory, is present. We don't know how to formulate quantum field theories that don't have that. So because CPT invariance, that CP violation or CP conservation corresponds to time conservation, which means that we can flip the time order. And flipping the time order means that initial and final get exchanged. So CP is roughly equivalent to T, and that means that this is equivalent to that. Okay. So with a little bit of CP violation, or even with a lot, because CP violation also involves interference between loop and tree level, this is often still a good approximation, even with CP violation. Okay, so we have this complicated result. Let me next start applying it to dark matter. So the thing we're going to be interested in is computing the evolution of the number density of the dark matter particle, together with, well, we're going to compute the interactions of the dark matter particle relative to the standard model stuff. So for my dark matter, I'm going to call my dark matter chi. And for now, it's not hard to relax this, but I'm going to assume that the dark matter is its own antiparticle. Again, you don't have to assume this. If you don't assume it, I'd have to write down separate Boltzmann equations for the dark matter species and its antiparticle. But for now, I'm just going to assume this to make my life easy. So suppose my reaction that interchanges dark matter with the standard model is just, I have some dark matter scattering, and the dark matter can annihilate with itself to make fermion-antifermion pairs. So for example, I have some Feynman diagram. So I've got chi-chi, and then I've got fermion-antifermion, and I have some diagram that looks like that. And this reaction can go forward or backwards. But we see that this reaction is going to change the number density of dark matter particles. And that's what we're going to be interested in for our Boltzmann equation. Now, in principle, I could also turn this diagram on its side. And this would also give me elastic scattering of dark matter of the standard model species. And the elastic scattering it's going to turn out that the elastic scattering typically is more efficient than this particle number changing reaction. And one of the things we'll assume in a second is that the dark matter stays in kinetic equilibrium, but not chemical equilibrium. So what we're primarily interested in is computing the deviations of the number density of the dark matter from its equilibrium form. But along the way, we're going to assume that the dark matter stays in kinetic equilibrium, so its relative momentum fractions are the same as it would if it were completely in thermodynamic equilibrium. So I'll come back to that in a second. But in any case, without touching any of that, the contribution of this term, delta C tilde, is minus, I have an integral over the two dark matter particles. And I have an integral over the final state phase spaces for the fermion and antifermion. I've got my 2 pi 4th delta, 4. I've got my matrix element for this. And then I have my symmetry factor. And the symmetry factor gives me a 1/2 because I have two identical particles here. But at the same time, this reaction also changes the number of dark matter particles by 2 units. So I multiply it by 2. So this is a symmetry factor. And this is the fact that this reaction changes the number of dark matter particles by 2 units. So these two things cancel. And then finally, I have my distribution functions of the two dark matter particles minus the distribution functions of the fermion and antifermion. So this is my collision term. And all right. So now I'm going to start throwing more approximations at you. That's going to make this somewhat more tractable. So the first assumption is that this reaction keeps the dark matter particle in equilibrium until the temperature falls below the mass of the particle. And I'll come back and try to justify this down the road. But for now, let's just assume that this reaction is fast enough that the number density of dark matter stays in equilibrium, at least up to temperatures of the size of its mass. And it's only after the temperature falls below its mass that it falls out of equilibrium. Yes?
I understand the factor graph and from our factorial thing.
Yes.
And but the two.
So the 2 is not technically in this equation.
Right.
So in this equation, I'm only changing the chi number by 1 unit.
Yeah. Oh, okay. Here.
So here I'm changing it by 2 units. So I put it in a 2. Okay. So my first assumption, and this assumption is valid for many of the cases we're going to look at. So my first assumption is that, well, I'm going to treat the standard model fermion. I'm going to treat the standard model fermion as essentially massless, and I'm going to assume that the temperature at which I depart from equilibrium is also a fair bit less than the mass of the dark matter particle. So it turns out that the upshot of that is that our Boltzmann, our distribution functions for the fermions, since the mass is much less than the temperature, and I'm also implicitly assuming that these fermions are in thermodynamic equilibrium, so they're just standard model particles, so they should be bouncing off photons like crazy, especially when the temperature is larger than their mass. These assumptions imply that FF is equal to FF bar is equal to the equilibrium distribution, for one. And also, with these relations, I'm going to treat the equilibrium distributions, E over T plus or minus 1, as being roughly just Boltzmann factors. Yes?
The elastic collision is much higher than the species, the reactions that change the species, right? What was the argument behind that?
Oh, I haven't made it yet. Okay. So I'll come back later and try to justify that. But actually, I haven't used that fact either yet.
Okay.
So I'll come back later, use that fact, and justify it after the fact. Yes?
And does the dark matter always stay in equilibrium with itself? It doesn't. So I suppose that once temperature drops down below its mass, it won't stay in equilibrium with photons?
Yes, yes.
But will it still, I mean, could it still like bounce off itself or like
Yeah, so the dark matter might have a larger, let's see. This is really the reaction of the dark matter bouncing off itself. The dark matter bounces off itself, and I suppose it could scatter elastically with itself.
so with F equal to chi? Or what?
Oh, sorry. So a different reaction could be dark matter scattering elastically off itself.
Okay.
What's going to end up happening, though, is that, just to give you the punchline, the dark matter number density, as it tracks the equilibrium, is going to become exponentially suppressed. So I start with a thermal dark matter density at temperatures much larger than the mass. The temperature falls. As the temperature falls, the dark matter equilibrium distribution becomes exponentially suppressed. And as that number density becomes exponentially suppressed, the rate at which dark matter can collide either with itself or with anything else becomes much smaller. So when that happens, the probability for two dark matter particles to collide with each other is going to go like n dark matter squared. So if n dark matter squared is small, that's really small. Whereas the probability for a dark matter particle bouncing along to collide with a fermion in the plasma, or some particle in the plasma, is going to go like n dark matter times n fermion. And n fermion is much larger than n dark matter. So this is roughly going to be our argument that kinetic equilibrium for dark matter by scattering elastically off standard model stuff is going to keep it kinetically equilibrated, even though its number density is not in equilibrium anymore. So again, I'll come back and cover this in more detail. I guess it'll be next class. But the idea is going to be that the dark matter still has an effective temperature equal to the photon temperature while it's going through this process. but its number density is going to start deviating from the equilibrium density. Okay. So I've run out of time. I'll come back to this tomorrow. But yeah, the upshot is that we're going to simplify this and write this as effectively a scattering cross-section times some dark matter number densities. And that will give us a relatively simple differential equation for the time evolution of the dark matter number density. And we'll see that this differential equation will, in some limits, push the density towards equilibrium. In the other limits, we'll see the deviation from equilibrium.